In last video lecture we had seen bimolecular elimination reactions, that is E2. Let us see unimolecular elimination reaction, that is E1. Today's topics are kinetic studies, reaction mechanism with energy diagram, orientation of E1, order of reactivity of alkyl halides, evidence of E1 mechanism, and factors affecting E1 and E2. So what is E1? E1 indicates elimination unimolecular reaction which proceeds through two steps. First step is the breaking of leaving group before the pi bond is formed, and it is a slow step and unimolecular. Why? Because it involves only one molecule, that is alkyl. Next, kinetics of E1 reaction. So E1 reaction follows the first order kinetics and rate depends upon only the concentration of the alkyl halide. Next, the E1 mechanism involves the two steps. First step is the ionization of the alkyl halide to form the carbocation and halide ion. And the second step is the carbocation loses the hydrogen and there is a formation of the alkene. In steps 2, the carbocation provide a pair of electrons to complete the octet of the electron deficient carbon, and these electrons are paired originally shared by the proton and made available through the pi bond formation by departure of the hydrogen atom. The rate of formation of carbocations that determines how fast a reaction goes, and once formed, the carbocation then rapidly react to yield the product and give the alkene. Okay, let us see energy diagram. In the energy diagram, first step is the loss of leaving group. So the energy diagram of E1 mechanism demonstrate the loss of leaving group as the slow step and with the higher activation energy. So in partially broken CBr bond, the bromide atom, being the more electronegative element, is partially negative charge and carbon is partially positive charge, and complete ionization of the bond leads to formation of the intermediate carbocation. So once the carbocation is formed, it is quickly attacked by the base to remove the beta hydrogen and forming the alkene. The smaller activation energy indicates the faster reaction. Okay, so this is the smaller activation energy in the transition state 2, and therefore it indicates the reaction is faster, and here the activation energy is higher and so it indicates the slow step. Okay, next, reactivity of even reactions. Okay, so in even reactions, as the carbocations are formed as an intermediate, these carbocations are favored in the tertiary, then that of the secondary, then that of the primary, and then that of the methyl. Okay, so secondary and tertiary carbons form more stable carbocation. Thus these formation occur quite rapidly. So if the reaction, that is even reaction, rate of even reaction increases as the carbocation, primary carbocation is less stable than that of the secondary and then that of the tertiary. So increasing the carbocation stability, there is a increasing the rate of even reaction. Okay. Next, orientation of even reaction. Even reaction is regiospecific because it follows the Sedgwick rule that states that the most substituted alkene is the major product. This infers that the hydrogen on the most substituted carbon is the most probable to be deprotonated. Deprotonated means the hydrogen atom is removed from the carbon and thus allowing for the most substituted alkene to be formed. For example, 2-pentyl tosylate, when reacts with the butyl hydroxide, it gives the 2-pentene and 1-pentene. But the most major alkene is the 2-pentene. Why? because it follows the Z rule, and that states that the most substituted alkene is the major product. Okay, understood? Next, evidence of even reaction. So even reaction does not show the isotopic deuterium effect, but it shows the rearrangement of carbocation. Okay, so intermediate carbocations have the property of rearrangement from a less stable to a more stable carbocation. This occurs either by 1,2 shift or 1,2 methyl shift. This means that the carbocation which is or initially formed, it rearrange itself to form a more stable carbocation. Okay, if the alkyl structure of the alkyl halide permits. So the carbocation form then loses the proton and it forms the rearranged alkene. This can be well explained by the rearrangement of the initially formed less stable carbocation to the more stable secondary carbocation by the 1,2 hydride shift. Okay, which then loses a proton and form the substituted alkene, that is the more stable alkene. Thus it may be noted that when more than one alkene can be formed, the preferred product is the more stable one and it follows the Z rule. Okay. Next, E1 versus E2 reactions. Kinetics. So we have seen in E1, which is reaction which determined by the substrate only. Okay, and in E2 it is determined by the substrate and base. Then substrate. Then what is substrate? The substance which is undergoing the reaction mechanism. Okay. So in E1, both the E1 and E2 reactions, the tertiary alkyl halide is more stable than the secondary and than the primary. Then Z rule. In Z rule, both E1 and E2 reactions follows. Okay. And base in E1 reaction usually not important, but in E2 reaction it is very important because the strong base should be there for the E2 reaction. Then solvent. In E1 reaction the solvent should be highly polar ionizing, and in E2 reaction the solvent polarity not important. Then rearrangements. Rearrangements, that is in E1 reaction the undergoes the rearrangement, that is the hydride shift, that is 1,2 hydride shift and methyl shift. Okay, and in E2 reaction there is no rearrangement of the carbocation. Why? Because there is not formation of the carbocation, but in E1 reaction there is a formation of the carbocation and hence it undergoes the rearrangements. Okay. Next, factors affecting E1 reaction mechanism. So in E1 reaction, the first factor that affects the reaction is the substrate effect, then base effect, then solvent effect, and fourth is the isotope effect. Let us see one by one. First is the substrate effect. So the order of the reactivity of the alkyl halide is tertiary is more stable than secondary and than primary. Okay, so this is because the rate determining step is the formation of carbocation and the stability of these ions increases as per the alkyl halide. Okay, then next is the base effect. So bulky bases favor the elimination of even reaction. For example, this alkyl halide reacts with the bulky base and gives these two alkenes, and more stable is the this one. Why? Because it is the more substituted alkene as per the Sedget's rule. Okay. Next, isotope effect. It do not show an isotope effect. This tells us that the CD or CH bonds are not broken in the rate determining step, and hence they are broken in the first step, that is in the reaction mechanism. That is the step number 2. Okay. Then orientation of elimination. Even reactions faithfully follows the Sedget's rule. This means that the major product should be the product that is the most highly substituted. Okay. So this is the example of the Sedgwick's even reaction mechanism. Next, factors affecting E2 reaction mechanism. First is the structure of the substrate, second is the strength of the base, third is the solvent effect, and fourth is the leaving group. Let us see one by one. First, structure of the alkyl halide. So structure of the alkyl halide, this is due to the stability of the more highly substituted alkene, that is as per the Sedgwick rule. Okay. Next, strength of the base. The base must be strong. Which of the following bases favor the E2 reaction or which favor the even reaction? Okay, so that will decide the base. If the base is strong, then which reaction favors? E2 reaction will be favor, but not the even reaction. Okay. Third, leaving group. The nature of the leaving group should be good. That is, the leaving group must be coplanar. Coplanar in order to form the pi bond. For example, ethoxide ion. As the size of the leaving group increases, the ability of the leaving group to leave increases. Okay. Then solvent effect. Polarity is not so important in case of the E2 mechanism because negative charge is spread over the transition state. Okay, understood? Okay. Thank you.